Okay, let me see if I can get this paper situated. All right, so today we're going to talk about interpretations and applications of the derivative and definite integral. And here's just some things that you need to know. So d dx of an amount is the rate at which that amount is changing. Okay. So, like if water is being drained from a pool, and R of T represents the amount of water measured in cubic feet, that's in that swimming pool any given time measured in hours, then R prime of T would represent the rate that the water is changing. Okay. So d dx R of T would equal R prime of T. So what would the units of R prime of T be? So now this is where you need to maybe pause and think about an answer and then come back and see if your answer is correct. But if this is in cubic feet measured in hours, right? Then R prime of T would be cubic feet per hour. So then if you took the derivative of the rate, if you took the integral, if you integrated the rate, that would equal the amount of change. So if thinking about this example with the swimming pool, explain what this value might represent. So think about what that might represent if you're talking about draining water out of a swimming pool. So from A to B, R prime of T dt would equal R of B minus R of A, which represents the amount of water that has drained out. From the pool between time A and time B hours. Oops, I can't spell hours. That's okay. All right, so that's what that would represent. So let's look at this table. We've got a table that is the velocity of a particle at a given time t. T is measured in minutes. So we need to approximate the value of 0 to 30 bt dt using a midpoint Riemann sum. Use correct units of measure. Explain what that value represents. So from 0 to 30, v of t dt would be about, okay, so that's going to be, they're going to be like 10 from 0 to 10. And the first midpoint is 1.6. And the second midpoint would be 3.1. And then the third midpoint would be 1.6. Forgot my calculator. It's not here with me. So that's 2. So that's 6.3 times 10. So it'd be 63. Now, this is the rate of a particle where t is measured in minutes. And this is feet per minute. So this would be 63 feet. And then explain what this value means. Well, from 0 to 30 of vt dt would be p of 30 minus p of 0, which would be, that's going to be the total change in distance from t equals 0 to t equals 30 minutes. And then the next question says, what's the value of 5 to 25 a of t dt? Use correct units, explain what that value represents. Okay, so a of t dt, if I was going to integrate that, then that's going to go back to the velocity. So from 5 to 25 a of t dt would equal v of 25 minus v of 5, which is 1.6 minus 1.6, which is, I don't need a calculator, 0 feet per minute. So that represents the amount of change in the velocity from t equals 5 to t equals 25 minutes. Okay. Move it up some. There's no one here to tell me. Can you move that? It's on the screen. You can't see it. All right, so let's look at this one. We got water in a bathtub. Got the temperature. So we're looking at temperature of the water, and it's strictly increasing. That's good. Twice differentiable. That's good. Where WT is measured in degrees Fahrenheit and T is measured in minutes. Okay, so this is what we have. Use the data in the table to estimate the value of W prime of 12 using correct units. Interpret the meaning of this value in context of the problem. Okay, so I need to estimate W prime of 12. So I'm going to go on either side of it and use 9 and 15. So W prime of 12 would be about W of 9 minus W of 15, which would be 9 minus 15. So that's about 61.8, 67.9 over negative 6. Gotta use my handy dandy Wabbit. All right, so it's going to be a negative 1.017 correct units. Okay, so think for a second, what should these units be? They're going to be degrees Fahrenheit per minute. And then it says interpret this meaning in the value or this value in the context of the problem. This is where some of you kind of fall apart. So what this means, oh, that's not a negative, by the way. Just kidding, I lied. It's not a negative. So what this means is at T equals 12 minutes, the temperature of the water is increasing at a rate of 1.017 degrees Fahrenheit per minute. That's what it means. And some of you confuse that, and sometimes you say something that's close to that, like it just increased by this amount. And I don't want to get all grammarly on you, but it's increasing at that rate, at the moment, at that exact moment. So at T equals 12 minutes, the temperature of the water in the tub is increasing at a rate of 1.1 per minute. That's what it means. All right, next it says, use the data in the table. Use the data in the table to evaluate zero or the definite integral from 0 to 20 of w prime t dt. Use correct units, interpret, blah, 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 all the same. So from 0 to 20 of w prime dt. Oh my gosh, look at that. This is why I don't like using pens. But I feel like if I don't use a pen, you're not going to be able to read it. You're not going to be able to read it if I don't get my big head out of the way. That would equal w of 20 minus w of 0. W of 20 is 71. W of 0 is 55. 16 degrees Fahrenheit. So what does that mean in context of this problem? That means from 0 minutes to 20 minutes, the temperature of the water went up 16 degrees. That's what that means. So 0 to 20 w prime t dt represents, I might try to move this to that side because then I'll be able to, the amount that the temp goes from to equal 0, 20 minutes. All right. Okay, so from 20 to 25, the function w that models the water temperature has a first derivative given by the function w prime of t, 0.4 square root of t cosine 0.06 t. Based on this model, what's the temperature of the water at time equals 25? Okay, so from 20 to 25, yeah, we're looking at 0.4 square root t cosine 0.06 t dt, and that would equal w of 25 minus w of 20. Okay, that's the one I don't know. That's my variable. That's the one I'm looking for. Okay, so this is going to be calculator. Just put that in your calculator, and you should get 2.043. W of 25 minus 71. And this 71 came from the chart that's at the top. So I'm just going to add those together. And there's my answer. Hold up a second. I got an email. All right. Good to know. Okay. Let's look at the next page, shall we? Oh, a pan of biscuits. I remember this from last year. I remember this problem from last year. It's rare that I remember something, but I remember this one. Okay, so a pan of biscuits is removed from the oven, at which point in time t equals 0 minutes. So like I take them out of the oven. Temperature of the biscuits is 100 degrees Celsius. Okay. The rate at which the temperature of the biscuits is changing is modeled by b prime of t equals negative 13.84 e to the negative 1.73 t. So first of all, find the value of b prime of t. So that's just a calculator thing. So just put that in your calculator and you should get that b prime of 3 is negative 8.236 degrees Celsius per minute. Okay, because it's a b prime, it's a rate. So that doesn't mean that's the temperature. That means 3 minutes after the biscuits are taken out of the oven, the temperature is decreasing at a rate of 8.236 degrees Celsius per minute. That's what that means. I'm not going to write that down because you can pause it and write it. It means 3 minutes after the biscuits are removed from the oven, the temperature is decreasing at a rate of 8.236 degrees Celsius per minute. Okay, so then the next one is to sketch the graph of B prime of T. So you put that in your calculator and you sketch it, and it looks something like, oh my goodness, I'm getting a lot of text messages because there was just some emails sent out, so sorry. And it looks something like this. That's B prime of T. Okay. And that represents, it says, explain the context of the problem, why this graph makes sense. So think about it. Why does it make sense since this graph is approaching 0? Why does it make sense that it has a vertical asymptote here, but a horizontal asymptote here? So just think about that for just like a second. And if you think about it, so B prime of T represents the rate at which the temperature of the biscuits is changing. So they're cooling down, right? Okay, so I take the biscuits out of the oven and they're going to decrease. The biscuits are going to decrease. And they're going to decrease until what? So, like, do you remember this from science? They're going to decrease until they get to like room temperature, okay? So they're going to keep decreasing until they eventually just level out. They're not decreasing anymore. But the temperature's not going to increase unless you put them back in the oven. But it's going to continue to decrease until they just level out and they get to whatever the temperature of the environment is. So that's why it makes that shape. They're removed from the oven. It's always going to decrease. It always has to be less than 0 because the temperature is always decreasing unless your house is, 450 degrees Fahrenheit, which you probably should move if it is. All right. At time T equals 10, what's the temperature of the biscuit? Show your work. So you're just going to go from 0 to 10 of this. And that's going to equal B of 10 minus B of 0. You know B of 0 is 100. You're looking for B of 10. You can put all this in your calculator, and you're going to get negative 65.817. Then you add 100. So 10 minutes after those biscuits come out of the oven, they are 34.183 degrees Celsius. All right, let's do page 525 real quick. All right, so you've got a cylindrical can with a radius of 10 millimeters used to measure rainfall in Stormville. During the first 5 days of a 60-day period, 3 millimeters of rainfall have been collected. The height of the water in the can is modeled by this function. Here it is from 5 to 60. It's right there. Find the value, use correct units. This is straight into your calculator, okay? What would the units be? If this is the rate in millimeters per day, then once you take the derivative of that, then it's just going to be millimeters. So you put this in your calculator. Your answer should be, I'm trying to keep this short because when they're past, the further I get past 20 minutes on the videos, the longer it takes them to upload, by the way. That's why I'm trying to rush through at the end. That's what it should be. And what that represents is the amount of increase in the height of the water level, the amount of increase in the height of the water level from T equals 10 to T equals 15 days. All right, and then at the end of the 60-day period, okay, so don't forget you'd already had 3 millimeters to begin with, okay? So you're going to have 3 plus from 5, put that backwards, from 5 to 60 of S prime of T dt, and that would equal 3 plus 163.565. That's just that in the calculator, which would be 166.565 millimeters of water. Okay. And then it says, what's the volume? This is just the height. That's the height. So volume is pi r squared times the height. So that would be pi times 10 squared times your height, which is 52,327.900 cubic millimeters. Wrong way. There you go. All right, try this one without me. Pause it, try it, read it. You've been given a rate. This one was really tough for people last year, so try this one. So let's talk about it. You paused it, you come back, right? If all the VIP people had stayed, so you got the rate at which this concert, they opened it, T equals 0. This is what you've got going on, measured in people. 100 people are already in the auditorium, so it's going to be 100 plus from 0 to 2 of this 1380 t squared minus 675 t cubed dt straight into your calculator. Oh, sorry, big head in the way again. Straight into your calculator. This is the setup. You already had 100 people in, and this is the change. 1,080 people. All right, I'll see you tomorrow.